Hello everyone and welcome to our very first video on this channel. So this channel is essentially a resource for students who are taking Organic Chemistry 1 or 2, and we will be closely following with the Stony Brook University curriculum. However, we are in no way affiliated with the university in any shape or form. So to begin, we will be starting with molecular orbitals. So the first rule is that pi or p orbitals, in this case I'll use them interchangeably, right, are drawn for carbons directly attached to a double bond. So for this carbon right here, this carbon, this one, and this one, we will be drawing a pi or p orbital. As you can see, this carbon down here, this very firstmost leftmost carbon, does not have a pi orbital drawn in it because there is no pi bond attached to it. The second rule, that these pi orbitals essentially are drawn for atoms that also resonate and are indirectly attached to a double bond. So for example, you can see this structure right here, right, has a resonance structure equivalent of this, right? And that means that this leftmost carbon, even though it's not directly attached to a double bond, in this structure, it is in this structure. And as a result, we draw the pi orbital on it. All right. For the third rule, we know that pi orbitals are also drawn for carbons that have a negative charge, essentially, right? So even though this does not have a double bond attached to it, we still include this carbon as part of our entire p orbital diagram. Hopefully that makes sense. Rule number 4 is that phases alternate at every node. So essentially, right, let's say we have one node here, which is this dashed line in the middle. These phases, right, so as you can see, black is on the bottom and white is on top, and then you have black on top and white on the bottom. They alternate, or they swap, every time there's a node. Our fifth rule is that no pi orbitals exist at nodes that intersect a carbon, right? So let's say here, we have to have one node. So essentially, we're trying to have this entire molecular orbital diagram be symmetric around the center, right? Not necessarily the center of carbon, but around the center. So in this case, if we want it to be symmetric around the center and we have one node, right, that means that we have to essentially remove this pi orbital for the symmetry. So we do not draw it. And the sixth rule is that the total amount of nodes is always n minus 1, right? And n is the number of contributing p orbitals in your compound. In this case, we have 3, right? 1, 2, 3. So n minus 1 is always going to be, in this case, 3 minus 1 is 2 nodes. So you're going to have 2 nodes in total at the most. I would do in this case, right, is find how many contributing pi orbitals we have. We have one here, we have one here, we have one here, and we have one here. That's 4. So n is equal to 4. So if we want to find how many nodes that is, it's going to be 4 minus 1 is equal to 3 nodes at most. So this diagram is perfect thus far. All right, next, I'm going to find how many pi electrons I have. So first, let me just quickly erase this so you guys can see. We have 2 here, and we have 2 here. So that's a total of 4 pi electrons. So 4 pi electrons. So starting from the very bottommost node, I'm going to add pi electrons in pairs of 2. So from 0 nodes here, I have 2 pi electrons, then here I have 2 as well. That is essentially me just drawing the pi electrons. Next, we're going to count from nodes. So the nodes always start at 0, which means that all pi orbitals p orbitals in this case, are in phase. So all the p orbitals here are in phase. In this case, there's one node, so there's 2 different sets that are in phase. And in here, and so on, right? So basically, you always start from 0 nodes, and you go upwards. Next, we're going to talk about what the HOMO and the LUMO here in this case is. So LUMO stands for lowest unoccupied molecular orbital, and HOMO stands for highest occupied molecular orbital. So our highest occupied molecular orbital will be the one at the first node. That's our HOMO. So it's going to be this diagram right here. That is our HOMO. This is particularly important for Diels Alder, which will be going on in subsequent videos. So for our next diagram, it's going to be the LUMO. In this case, right, the LUMO is the lowest unoccupied molecular orbital. So as you can see, there are no electrons occupying this molecular orbital, and there's two nodes there. Hopefully that makes sense thus far. Let me erase all this once more time. This way we can look at the actual division of the nodes. So here there's 0 nodes, so we can ignore that. This one node. So we want, remember, we want symmetry. Essentially we want it to fold in on itself perfectly. You could say like a book, for example, if that makes it more understandable. So we have one node and we'll put it directly in the center. Here we have two nodes. So with two nodes, you might ask, all right, why don't I just go through these orbitals, right, and call it a day? Well, that's kind of like a seventh rule that we didn't go over, but essentially you want to keep as many orbitals as you can, as well as be symmetric. So symmetry is always number one. Number two, try to keep as many orbitals as you can. In this case, we can keep two orbitals by just slicing these bonds in the middle instead of making it go through them. So that is what we're going to do. And with three, right, we can make this symmetrical by cutting each bond once, right? And remember, right, every time you have a node, the phase will switch, essentially, right? So this is black is on the bottom, black is on the top, black is on the bottom, black is on the top. Hopefully that makes sense. So let's continue. So practice question number one, right? So we have this structure right here, and I already outlined which of these carbons will have a pi orbital or p orbital coming out of it. So as you can see, right, this can also be interconverted as a structure as so, right? And how do I do that? Well, I just push this carbon, this double bond here. All right. So as you can see, you have this carbon, and this carbon. All three are part of this molecular orbital diagram. Hopefully that makes sense. So we have one, two, three. Next, let's quickly do the electrons before we start shading. So we have two pi electrons here total from this double bond. So I'm just going to put one here and one here. That's two. All right. So from there, we already know what our HOMO and our LUMO are, right? So this is always going to be our HOMO, and it's always going to be our LUMO. And the reason is because this is the lowest unoccupied, and this is the highest occupied. That's pretty much it. LUMO and HOMO, they're really easy to get after the first few practice problems. And then next, we're just going to shade. So to start, right, this one has 0 nodes. So this one can be shaded as black, this one can be shaded as black, this one can be shaded as black. Perfect. This has one node. So how would I draw it with one node? Well, I would go through this orbital, so this orbital would not exist, right? I would not draw it here. And this could be black, and this will be black because of the alternation. But for two nodes, right? In this case, we could just draw them right here and right here. And as I said before, right, there's an alternation. 1, 2, 3, every time there's a node. Now, are we going to draw 3 nodes in this problem? In this case, the correct answer is no, we will not. Why? Because of the n minus 1 rule. In this case, n is 3. So at most, we're going to have 2 nodes. Hopefully that makes sense. Let's continue. All right, so for this question, once again, we can start with how many nodes will we need, right? So we have how many participating pi orbitals? Well, we have one here. That's 1, 2, and 3. So n is equal to 3 minus 1, and that is 2. So 2 nodes, right? Next, right? How many electrons do we have? Well, let me erase this. So we have these two electrons here, that's two, and we have these two from the anion here. Now, what you can do is, if this seems a little confusing to you, is you can bump up these electrons, right, up onto this carbon, right, through resonance. Essentially, these electrons collapse down, and these electrons come up, right? So it's going to be giving you this type of structure. As you can see, it's right. You could flip it over. It's exactly the same structure. But basically, that's the point, right? You have four electrons that are participating in this struct in this 4 pi electrons, right? So we will start with 1, 2, 3, 4, right? Here is going to be your LUMO, and here's your HOMO, right? And then from there, we're just going to go by nodes. So 0 nodes, they're all colored. 1, 2, 3. 1 node, well, this one would go straight down the middle, deleting this one. We get 1, 2. And for 2 nodes, right, we would simply, in this case, 1 here and 1 here. And that is it for this question. So with this problem, you're basically doing the exact same thing. It's just going to be a much larger molecular structure. So as you can see here, we have 1, 2, 3, 4, 5, 6. So n is equal to 6 minus 1, that's 5. So 5 nodes in total. I didn't draw out all 5 because I wouldn't be able to fit it on this page. But hopefully you can, with practice, draw out all 5. So to start, right, they're all going to be at 0 nodes. Well, actually, before we even do that, let's just quickly get the electrons out of the way. We know we have 6 electrons total. I'm just going to do 1, 2, 3, 4, 5, 6, right? So our HOMO is occupied right here, and our LUMO is going to be up here. And I know I didn't go over this in the previous slide, but the higher you go up, right, the greater the energy. Hopefully that makes sense, right? Less stability, more energy, right? More willingness to react. So 0 nodes, they're all in phase. 1, 2, 3, 4, 6. 1 node. Now, where would I be able to put this 1 node? Make symmetry. Well, in this case, it's just right here. 1, 2, 3, right? 1, 2, 3. 2 nodes. Where would I put the 2 nodes to make symmetry? Well, in this problem, I would just put them right here. 1, 2. Where would I put 3 nodes? Well, with 3 nodes, right? Remember, we want symmetry among the center. So I can put 1 node right here, 1 node right here, and 1 node right here. Hopefully that makes sense. To reiterate, what do you do with these problems? Well, remember, you're starting from 0 nodes and you're going all the way up. So to find your peak, how many nodes should I draw up until? Well, if you're doing this for Diels Alder, really all you want to do is up to LUMO. You don't want to really go past LUMO. Just a waste of your time. But you can if you want. You could draw out 4th and the 5th nodes, right? Essentially, right, I draw out 0, 1, 2, 3 nodes, draw out these blank diagrams, right? Then you can draw in the pi electrons, 2, 2, 2. In this case, there's 6 electrons total, so 2, 2, 2. You know your HOMO is going to be the highest occupied, so that's your HOMO, that's your LUMO. Boom, you already found your HOMO and LUMO. Then it's just a matter of nodes and shading. So with this problem, right, you got this disgusting structure right here. Now, hopefully you can realize that I can simply propel these electrons here and these electrons here, and I can make a similar resonance structure of like so. So that's just a very terrible resonance structure of this image up here, right? And with that, right, you know that the contributing pi orbitals are right here. You have a total of 4. So that's how you get that. Then once again, so how many do we have in pi electrons? We have 4, right? So 4 electrons total. So with 4 electrons, instantly we can go 1, 2, 3, 4. This is our HOMO. This is our LUMO. And then from there, it's the same old, same old. You have 0 nodes. You have no nodes, so we're just going to all in phase. 1 right down the middle. 2. Now in this case, once again, boom, boom. Remember, you want symmetry among the middle, as if you folded it like a book, right? And with 3 nodes, 1, 2, 3. Beautiful. Now hopefully that makes sense. Last question, number 5. So there's nothing new in this problem. All there is just more work for you to do. Now, from the beginning, we notice how many participating p orbitals do we have? Well, we have 1 here, 2, 3, 4, 5. So 5 total. So n minus 1, that's 5 minus 1 is equal to 4. We have 4 nodes in total. So 4 nodes in total. Well, I have perfect. I drew them all out here. How many pi electrons do we have? Well, let me remove all the ink. So we have 2, 4, 6. So 6 electrons, right? So I go down, up. There we go. So what is our HOMO? So our HOMO, once again, is going to be right here. And what is our LUMO? Up here. And now the last part you have really is just drawing in these nodes and shading. That's pretty much it. So this is all in phase once again. With one node, we will be removing this center, right? With 2 nodes, right? In this case, we would be removing this one and this one. With 3 nodes, we would be removing, we wouldn't have to remove as much as with 2 nodes, but we would be removing the center node right here. And with 4 nodes, even though we don't need to, in this case, to find the LUMO, we'll still draw it out. It's just going to be 1, 2, 3, 4. Nothing fancy. That's pretty much it. So we're starting from 0 nodes and we go up 1. Remember, if I cross through it, that means it's deleted. I just didn't delete it in this to show you how I would start from scratch, right? 2 nodes, 3 nodes, and 4 nodes. Hopefully that clarified molecular orbitals for you. I really hope that helped, and I'll see you next video.